Okay, welcome to another video on applied electricity. So we are going to be solving the applied electricity first semester examination for 2023-2024 academic year, right? So we are going to be solving that promotion. I've finished all the solutions on first semester examination 2022-2023 academic year. I've uploaded all the videos onto YouTube. There are actually 4 parts videos on that. So we are going to today, I'm going to look at 2023-2024 academic year applied electricity final year examination paper. So if you haven't watched the 2022-2023 year paper solution, you should actually go and watch that one before you watch this current video. Why? Because it's going to help you understand more, because most of the questions that I've solved, you are going to see similar questions here, right? So it's the same method that or formulas that we are going to be using to solve the first 30 questions, right? The first 30 question, meaning question 1 to 30. Now, starting with question 1. So let's get started. We have question 1 here. Question 1. Equation which measures alternating voltage. Okay. When you have an equation, so this just to tell you which of these equation is an alternating voltage. So if you have an alternating voltage, right? If you have an alternating voltage, we know the general expression is what? The instantaneous voltage, use small letter v, is equals to the maximum, right? The maximum voltage sine omega t, the angular frequency, then plus or minus the phase angle. So that's the general expression. But you can see here the equation here. So if we have the phase angle to be 0, then this just becomes a simplified version of the general expression. So we have sine omega t, right? So we have this. So you can see this is the same as what? The first part here, right? Theta here is equals to what? Omega t, right? So that represents theta. So the answer here is A. Now, question 2. Dash waveform is a periodic waveform which interchanges between positive and negative values. So this is talking about definition, right? You can see A, we have direct, B, alternating, C, sine wave, and then D, rectangular. So this here is going to be B. Why? Because when we talk about alternating waveform, right, it interchanges between positive and negative values, or it alternates between positive and negative values. So sine wave and rectangular wave, they are both, all of them are alternating voltage. So the correct answer here would be alternating waveform, right? Alternating waveform. The time taken, question 3. The time taken for an alternating quantity to complete one cycle is called, so the time taken to complete one cycle, for example, you have a cycle which is 2 pi, a complete cycle is 2 pi. So the time that is going to take for you to complete, right, this full cycle, which is 2 pi, we refer to that as what? The periodic time, right? T, which is a period or periodic time. So the answer here is A. Question 4. Instantaneous and average values are represented by, when it comes to instantaneous values, like here, that you can see I'm using small letter V here, right? So for instantaneous value, we use small letter V to represent the voltage. Now when it comes to what? Average values. Average values, we use capital letter V, and then we blow it, we write here average value. So meaning here is voltage, this is voltage, so mean average voltage. So for instantaneous, we use small letter, and for average value, we use what? Capital letter, and then we write average value below it. So the answer here, so here you look at in terms of what? Respectively, right? So instantaneous is small, and then average value big letters. So we get respectively, we get D. Answer here to be D. Now question 5. The root mean square is another name for the equivalent heat effect of AC and DC. So here the answer is true, right? When you talk about root mean square, it's also the equivalent heat effect, or the power, right? The same power that is going to be dissipated by a DC current as what? An alternating current, right? So I mean, we are looking at the value of what? The values or parameters that will dissipate the same amount of what? Power, right? The same amount of what? AC power as what? Relative to a DC power. So here the correct answer here is going to be true, right? Everything is the same name for the equivalent heat, so it's A. Now moving to question 6. All are the names given to the largest value reached in half a cycle. So if you have, this is question 6. So all these are to do with what? The largest value reached in half a cycle. So you can see even with the diagram here, this is half a cycle. So this is half a cycle here. I think I have to use a different color for this. Maybe this one. So this is, let me use different color. Okay. So this one. Okay. So the name given to the largest value here, remember we have what? A minimum. No, the minimum is a down one, so it's not the largest, that's actually the minimum. So then the next possible answers, we have B maximum value, C amplitude, and then D peak value. See, all this refers to what? The largest value, right? So we can call it this one, let's say we have V, call it the maximum voltage, right? Or the peak voltage, or the amplitude. So the answer here is what? A. That's the only one that is not used to refer to the largest value reached in half a cycle. Now moving to question 7. For a sine wave, let me make this much bigger a bit. Okay. For a sine wave, the average value is, So average value, this is just to see whether we know the formula for average value. I wrote the formula the last time. Average value, let's say for average value is going to be equals to, right, is going to be equals to 0.637 times the maximum value, right? Maximum value. So the answer here is going to be 0.637 times the maximum value. So it's A. Okay. The answer here is A. Let me change. I don't know. I'm not even okay with this one here. So this is it. Now moving to question 8. The process of obtaining unidirectional currents and voltages from alternating currents and voltages is, this one is what? Rectification. So you can see the first one, A, is what? Rectification. You have to pay attention to the names there. Then B is reluctance, C rectification, D reversal. So the answer here is C, rectification, right? So it's a process by which you convert an alternating voltage to a direct voltage, right? So that rectification. Now moving to question 9. Graph of alternating current is A. So if you have a graph of alternating current, right, that's AC. How does it look like? You can see here we have a cos wave, B tan wave, C curve, and then D sine wave. So it's sine wave, right? All this alternating current that you've seen is always what? A sine wave. We experience a sine wave. Now question 10. Steady DC voltage is also known as steady DC voltage. So meaning we are referring to what? Effective voltage, right? Effective voltage. Effective voltage, which is the same as steady. You can say steady DC. And effective voltage is another name for what? Root mean square value, right? Root mean square value. So the answer for question 10 is going to be C, root mean square value. Now moving to question 11. Question 11. Highest point on AC graph is known as, here the highest point. If you have an AC graph, meaning if you have an alternating current, for example, let's say this was to be current. Let me make this into a current. Right, let's say this was to be current. Okay, let me go and see where is my, oops, I don't know what happened. Okay, then let's say this is current, right? So if this is my current, then the highest point in the AC, we refer to this point here as the what? We call it the peak value, right? The amplitude, frequency, and then here we have what? Frequency, and then D we have waveform. So we have here to be waveform. So that was question 11, right? So with this question 11, actually, when you look at this, you see that we call it what? A peak value, right? Which is A. And then we have B here to amplitude. So this one is also correct. So it's both A and B, they are both correct, right? So meaning if you pick any of this, I think in the when we were correcting this, I think that's how we did it, right? If you select either A or B in question 11 here, you are correct. Okay. Now moving to question 12. Which of the following can measure an alternating current? So you want to measure alternating current. What instrument can you use? So we have a voltmeter. No, voltmeter is to measure voltage. So here we are dealing with current. So you have to pay attention to, we are talking about current here. So B is ammeter. So you can see here the answer will be what? Ammeter, right? Use ammeter to measure current. Now moving to question 13. An alternating EMF is given by 400 sine 100 pi volt. The root mean square value of the EMF is, here you are just to find the root mean square value, and the formula is, meaning this is question 13. The formula here will be for voltage, right? So root mean square will just be 0.707 times the maximum value here, which is voltage. So maximum voltage, now we are going to get 0.707 times the maximum voltage here is 400. Okay, so we have here times 400. So I'm going to multiply. I'm using my calculator. I'll multiply 0.707 by 400, and that gives me 282.8 volts. So the possible answers, you can see we have B, which is 282.84. So it's what? B. Now moving to question 14. The ratio of the mean value over half a circle to the root mean square value of an alternating current is. So if you are having so if you will take the ratio of the mean value over half a circle, that's what we just refer to as what? The average value, right? So you take it over half a circle. Average values, for you take them over half a circle, because if we take over a full circle, you get a zero. You get zero because we are dealing with alternating voltage. For example, this here, when you talk about average voltage, we take it over half a circle, meaning 0 to pi. We don't take it over a full circle. If we were to do that, the average voltage becomes 0. So let's look at, because we are doing alternating, right? So the positive and negative side are going to cancel out, so you get 0. So let's look at this. We have to take what? The mean value to the root mean square value. So this has to do with ratio. It's similar to saying 1:2, right? Which you can make it to be, maybe express it as 1/2. So we are going to use that idea here. So if we are to take the ratio of the mean value or the average value, and let's say here we are talking about current, I'm going to use current. Like, let's say we are talking about the average current. So let's say I have my average current to be, and the formula again, you just 0.637 times the maximum current. Okay. Now that of what? The to the root mean square value, and we know root mean square value. So in terms of what? Root mean square value for current is going to be root RMS equals to 0.707 times the maximum. So we have to find the ratio of these two. So I'm going to take one, like we did here. I'm going to take from the question, we take the ratio of what? The average value, which is what? So I'll take 0.637. Okay, or let me just write it this way, to what? Average value here to that of one, the root mean square value, so that we replace them. Here is 0.637 times the maximum current, or the maximum value. Then we have here will be 0.707 times the maximum value. So you see, these ones will cancel out. Here we have to now express this in a fraction form, right? And this based on the formula that I didn't drive the formula, right? But what you end up happening at this 0.63 comes from what? It comes from 2 divided by pi, okay? 2 divided by pi. And then the 0.707 is the same as 1 over root 2, okay? So if you take 1 over square root of 2, you get 0.707. So I'm going to simplify this. So this becomes 2 over pi times, you bring this up, right? So root 2 here over 1, okay? You take the reciprocal. So this is mathematics. So you end up getting what? 2 times square root of 2 to 1. So you can see the answer in terms of ratio now will just be what? 2 times square root of 2 is to what? 1. So the answer for this, okay, no, here, sorry, remember here is pi, you multiply by this, so you get pi. Oops, so here we pi rather, so that we get this pi. Get pi, okay, here is pi. So the answer here becomes B. In an alternating current, that is question 15 now, right? Question 15. We are moving to question 15. In alternating current, the direction and magnitude of the current varies. A, randomly, B, periodically, C, exponentially, and then D, do not vary. If you look back again, you can see here, right? In terms of this, it varies periodically in terms of time. Remember, we even have T here, right? For a complete circle, we look at the time. So it tends to vary periodically when we talk about an alternating current. So for question 15, the answer here is B, or periodically. Question 16. Ghana has a root mean square value of Ghana. So root mean square value is the voltage you get from the electricity company. So in Ghana, it's going to be the voltage we get from ECJ, and it's tend to be equals to what? 240, right? We get 240 volts from ECJ. So that is the root mean square value. Question 17. Alternating current AC cannot be measured by DC ammeter because AC cannot pass through DC ammeter. No, that's not the reason. Then B, average value of complete circle is 0. C, AC changes its direction. D, none of these. So you see that the answer here is going to be what? B, right? Why? Because if you are taking the average value and you are using, in this case, a DC ammeter, right? DC ammeter. So when it comes to the voltage, right? So the average voltage for that, in that case, is going to be 0, right? It's not going to be able to incorporate the fact that average value, when you are trying to find the average value, you take it over what? A half a circle, right? Half a cycle. So the answer here will be B. Which of the following value of current is minimum for the alternating current? Question 18, right? Which of the following value of current is minimum for the alternating current? So here we're talking about minimum value here. So meaning mean value, right? So as the name applies, is going to what? Okay, for minimum. So here, okay, it's not going to be mean value per se, but we are going to be comparing the values, right? So who the following current is minimum for? Sorry, it's not mean value here. Very good. You can see mean value here is what? The average value, right? The average value. So how do we do the comparison? We compare and see which of these is going to be the minimum or the smallest value, right? That's what this is all. So if I given peak value, we know peak value is the same as what? The maximum value, meaning Vm. So we can say, we know that Vp is equals to what? Vm, right? Now when it comes to we compare that, right? Now B, which is root mean square value, and that one too we know in terms of the maximum value. So let's say in terms of voltage, here we have maximum, the root mean square voltage is what? 0.707 times the maximum voltage. Now we go and write the formula for mean value, which is C. C is also mean value, and mean value is the same as the average value. So that means I have here to be my average value, which I wrote these formulas earlier. 0.637 Vm. And then the last one is peak to peak, right? Voltage. So that will be what? Twice the maximum value. So if we're to compare these four parameters, right? So, and which of them among them is going to be the minimum? I mean, you're going to have the smallest value. If you are comparing, for example, peak value, which is the maximum voltage Vm, you compare that to what? To root mean square value. You can see that relative to that, Vm is going to be what? Higher, right? Because it's, when you look here, you have 0.70 times the maximum. It's just a fraction of the maximum value. So here the minimum, when you compare the peak value and the root mean square value, is going to what? The root mean square value. Now we compare the root mean square value with what? With the mean value, which is the average value here. Again, when you compare this, you can see that it's also the mean value is also a fraction of what? The maximum value. But when you compare them, 0.70 and then 0.637, right? Which one is what? The smallest. You see that the smaller one is going to be what? The 0.637 times the maximum value, which is the mean value. Now if you even compare this now to what? The peak to peak, which is twice the maximum. So the minimum here, or the smallest value here, is going to what? C, right? The mean value. Now question 19. The form factor is here. Form factor, meaning you have to know the formula for form factor. We saw the same question, right? And 2022-2023 academic year questions. So this same question was there, and the answer was what? For form factor, we take the ratio of what? Meaning the form, meaning we take the root mean square value. Let's say if it's voltage, to the what? The average voltage. So this became, so that's the formula. So when you look here, the answer here of what? Root mean square value to average value, which is B. Now moving to question 20. The peak value of a sine wave is 200. Its average value is, so here we have to find the average value, and I wrote the formula, right? So I'm going to just write the average value here is voltage, right? Meaning average voltage is going to what? 0.637 times the maximum what? Value, which is 200, the peak value, which is the same as the maximum value, so times 200. So I'm doing the calculation. We have 0.637 times 200, 637 times 200, we get 127.4 volts. So the answer here becomes A. Which of the following is a correct representation of peak value in an AC circuit? So which of them is it? So let's say you want to find a peak value. Which of this here is the right formula? We have let's think about what peak value, right? And even if you are looking the answer, you can see we have peak factor, right? We have root mean square value over peak factor. We already know the formula for what? For form factor, right? The form factor, which is what I wrote here, you can see is what? Root mean square value to the mean value, right? But we don't know about form factor, the peak factor. So let me write the formula for peak factor. For peak factor, the formula is what? You take the what? The maximum voltage to the what? The root mean square value, right? So if we were to make the peak value, which is the same as the maximum value, the subject here you get will be equals to peak factor times what? The root mean square value. So we look for this answer. You can see that when you check well, you realize the answer here will be what? D, right? Where we have root mean square value times what? The peak factor. Okay, peak factor. So if you look at the other ones, they are wrong, right? Like here, A, root mean square value times divided by peak factor. That is wrong when you make it a subject. So we get here to be D. How many cycles will an AC signal make in 2 seconds if its frequency is 100? Again, this question too, we saw a similar question under the last paper I solved, right? We saw a similar question. So here we are given the what? The number, the time, right? Then we are given the frequency, and you are asked to find the number of cycles. We know frequency, F will be equals to what? Number of cycles over time. So here we are given frequency we are given time. So let's make number of cycles the subject. So this becomes number of cycles. It's just going to be frequency times what? Time. And the frequency, as you can see here, is 100. And the time is 2 seconds, right? So we get 200 cycles. So the answer here is 200. Okay. Now moving to question 23. In an alternating current AC, the direction and magnitude of the current varies. Again, this is just repeated, right? It varies what? Periodically. We already saw this question. This is a repeated question. Now moving to, and then question 24. For a sine wave, the average value is, this one is also repeated, right? So there was a mistake here, 0.637 times the maximum value. Now question 25. Impedance triangle is generated from voltage triangle by, again, this one is under chapter 10, right? So if you have a voltage triangle, right, you get the impedance triangle by dividing by current. Why? For example, let's say I have my voltage triangle to be this way, right? I have this. Let's say this is VL, right? Here is VR, and then here is V, right? Now, to get, because here, let's say we are looking at the case whereby this, I have my inductance being series with what? With a resistor, right? So we have something of this nature. Okay. So we have this nature. I have my alternating voltage. So this is the resistance, this is the inductance, right? So if we're to get the what? So we have this is the voltage across the inductor, this is the voltage across the resistor. So we get, let's say, this kind of. So you can see with this kind of circuit diagram, because the resistor and the inductor are in series, so the same current will pass through them, right? So when you come to the voltage here, VL is what? Is going to be the current times what? The inductive reactance, right? VR will be what? The current, which is, they are all the same, times what? Resistance. And then the voltage supply, right? Voltage supply here is the current times what? The impedance. So you can see that if you divide each of this side by current, you end up getting what? Only resistances, right? So let's get something of this nature. Here you divide by current, get Z. Here you get what? SL. Here you get what? R. So this is what we refer to as the what? The impedance triangle. And the first one is the voltage triangle, right? So we get this by dividing by current. So the answer is B. A difference of 180 degrees between phases is known as antiphase. Yes, so we refer to this as antiphase. So if you have two waves and the phase angle is 180 degrees, we refer to this as what? Antiphase. Right? Now question 27. A 200 volt 60 Hz supply is applied to a capacitive circuit. The current flowing is 2 amps and the power dissipated is 150 watt. What is the resistance? Here we are talking about a capacitive circuit, right? But this is not the same as what? A purely capacitive circuit. So you have to know the difference. This is a capacitive circuit. Meaning with the capacitive circuit, we factor in the fact that the capacitor cell has some resistance, right? So with this question here, if I have a capacitor, right, a capacitive circuit, say I have a, so we have, for example, I have my capacitor, right? So we factor in the fact that this capacitor is also having resistance, right? So we have R here, then we have our voltage supply, which is alternating voltage. We have this kind of question. So with this, you can see that we are being told that the current flowing is what? 2 amps, meaning the current here is 2 amps. And then the power dissipated is 150 watts. So the power dissipated here, you can see it's in watts, meaning it has to do with what? The resistance, right? Meaning this power dissipated is talking about the what? The power dissipated by the resistor, right? The resistance. So this power, so power dissipated by a resistor, right? You know the formula to be what? Power dissipated by, let's say, a resistor is going to what? We take the current that is passing through the resistor, right, times its resistance, right? Its resistance. So with this question here, if you look at this, you can see that we know the current, which is what? 2 amps. That will be the current that is passing through the circuit. So IR here is 2 amps. And then we are giving also the power. So we just make resistance here the subject so that we get power over what? So we get power to be equals to resistance will be equals to the power PR divided by IR squared. So resistance here becomes, the power is 150 divided by the current, which is 2. So 2 squared, that will give me 150 divided by 4, which is 37.5 ohms. So the answer here, when you look here, is going to be what? A. Now moving to question 28. So 28 here. What is the capacitance in the circuit in question 27? So Q27 here referring to what? Question 27 here, right? Question 27. So now we go back to question 27. We try to find the capacitance. So again, that's why it's important when you sketch the circuit diagram, right? Because it allows you to see everything clearly. You can see now with our circuit diagram, if I want to find the capacitance, we are given the we are asked to find the one, the capacitance, right? The capacitor. At the same time, you know this is our what? Capacitor, which is C, right? We use here capacitor. So the capacitance, I'm using C to represent the capacitance, right? You see, which is what we are interested in finding. Now, if you look at this very well, you can see the current, the same current is passing through what? The capacitor and the resistor, because they are in series, right? So because of this, we can write the voltage across this capacitor, right, is going to be equals to, meaning let's say VC equals what? The current which is passing through, meaning IC, times its what? Resistance. And this resistance, the resistance here we call what? Reactance, times this reactance here. So we get this. So you can see now I can make reactance the subject, and we know that reactance to relates to what? Capacitance, which is 1 over capacitance times what? Omega, which is the angular frequency. And then we can simplify to be what? capacitance times angular velocity in terms of what? Frequency is what? 2 pi f, right? 2 pi the times the frequency. So you can see now I can first find for capacitance for reactance, right? Reactance of the capacitive reactance, which is XC, will be equals to the voltage, right? Voltage equals to VC over 1 IC over IC. But when you look, well, you see I don't know the VC even. We don't know the voltage across the capacitor, right? So what that means that we have to calculate for it. And to calculate for the voltage, right? Calculate for the voltage, we have to now make use of what? The voltage triangle, right? Voltage triangle. So if I have a capacitor and then it is here with what? A resistor. So that means I can write here, the current is the same, right? So we have current, and then when it comes to the voltage, right, that is going, the voltage across the resistor VR here is in phase, right? You have to know this, it's always in phase with the current which is passing through it. So I can write it on the same place, which is VR. Now when it comes to the capacitor, right, the current which is passing through, let's say IC, right, is 90 degrees. It leads the current by 90 degrees. So you put here 90. I have 90 degrees here. Right, here it is also IC. Okay, let me put here. IR is equals to IC. So we have this to be our VC. Okay, so here actually the diagram is supposed to be going down, right? Because we are dealing with it's rather lacks the current by 90 degrees. So let me just do it very well. Though we get the same answer, but it's better we get the diagram should be accurate. So here, like I said, you have your current R, and then your voltage is going to be in phase with your voltage. Now when it comes to this is also the same as IC because they are in series. Now the voltage across the capacitor is going to lag the current IC by 90 degrees. So we have here to be 90 degrees. So once we've done this, now you make a triangle of this nature and you indicate here to be your phase angle. Now I can label here, which is what? VC, right? Now here become our voltage supply V, right? Voltage. So now I can write here V. We apply Pythagoras theorem. V square will be equals to VC square plus what? VR square. VR square. And from the questions, we are given what? V, right? We are given the voltage supply to be 200. Now when it comes to VR, can see that I can calculate for the voltage across the resistor. Why? Because we know the current which is passing through, and now we know the resistance, right? We know the resistance. Or even I could even use this and the impedance triangle so that I'll get this straightforward, right? Could have used it, but since we have already done this, let's just continue with this. VR, let me just write VR, which is will be equals to the current R times its resistance. So the current here is the same current, so the current is 2, and the resistance which we got was what? 37.5. So here the voltage becomes this times 2 37.5 times 2, then I get 75 volts. So I get 75 volts. Now I can find VC, which is going to be square root of V square minus VR square. So we get it to be, the voltage supply is 200 square, VR is 75 square here. So what do I get for this? So I have 200 square minus 75 square, and then we take the square root. So we get 185. So VC here becomes 185.40 volts. Once I've gotten this, I can now calculate the capacitive reactance, right? Which is C will be equals to VC over IC. So I now have 185.4 divided by, again the current is 2. So this divided by 2. So I get this to be negative 2.70 ohms, right? Ohms. Now, once I've gotten this, but we are not done yet, right? Remember, we have to find the capacitance. So I come in back to this formula I wrote here. Then we make capacitance the subject, right? So capacitance here will be equals to, so if we were to make capacitance the subject, so you can see, meaning we multiply by capacitance, and then so here the capacitance will just be equals to C here will be equals to 1 over capacitive reactance 2 pi F. So that gives me 1 over, isn't it 2, right? 82.7 times 2 pi times the frequency. Frequency is given from the question, which is 60, right? 60 hertz. So once I've done this, let's see what we are going to get. Yes, everything, right? So meaning here times 2 pi times 60. Then take the inverse. So when you do this, you get the capacitance to be equal to 2.861, okay, times 10 to the power minus 5 farad. So when you look at the possible answers, you can see that they are expressed in what? Microfarads, right? So meaning, let's change this to micro. So you get here to be, so we have to get minus 6, so that will just be 28.61 microfarad. So we get the answer here to be 28.61, which is C. Now moving to question 29. A capacitor is connected in parallel with what? A resistance R across a 60 across a 60 volt 100 hertz supply. The supply current is 0.6 amps at a power factor of 0.8 leading. Calculate the value of R, right? The value of R. This question is the hardest question under this section, right? It's the hardest question under this section. Here, again, we pick this question, we analyze it. So we have question 29, step by step. Question 29, step by step. So here, you are having a capacitor. It's in parallel with a resistor. So let's say I have a capacitor here. So, and then I have it being in parallel with what? A resistor. This way. And then across a 60 volt. So meaning we have here an alternative voltage, which is, and then the voltage supply V here is which is 60 volts. Now, so here is the capacitor and here is the resistor. So a 60 volt meaning 100 hertz. Okay, that's the frequency. The supply current is 0.6 amps. So here 0.6 and here is 0.6. That's the current supply. I here is 0.6 amps. So we are asked to find the resistance. So we have to find the resistance here. And not only that, we are also told the supply current is 0.6 amps at a power factor of 0.8 leading. Calculate the value of R. So here, power factor. Again, you have to know this formula for power factor. Power factor is equals to the active power or the true power over the apparent power. So this is the formula. Active power here is usually the power we are looking at, the power dissipated by the what? The resistor, right? The resistor. And we look at this power in terms of what? The apparent power. So let's say you have normally the apparent power is going to be the power supply times what? The voltage supply. Then the formula for active power in terms of the supply powers, the current supply and the voltage supply is going to be their product times what? Cos times cos phi, which is the phase angle. So because of that, when you replace the formulas, you get here to be, get this formula. So this will cancel, and we just, again, we can write power factor, which is PF. Yeah. So it equals what? Cos phi, meaning cos of what? The phase angle. Cosine of the phase angle. So this is the formula. Now, how do we use this to find the resistance? Now, by looking at this, we know that power factor is 0.8. So it means that the answer, this one will give us 0.8. So based on this, you see that I can find the what? The active power, right? Which is P. We know that P is going to be equals to 1. Based on this formula, it equals to power factor times what? The apparent power, right? So the power factor, which is 0.8 times the apparent power. But before I even write the power, you can see that from the question we are given the what? From this question here, we are given the power supply and then the voltage supply. So I can even calculate I can calculate here the apparent power, so which is going to be the product. So you have 0.6 times 60, which gives me 0.6 times 60 is going to be 36. So that will be 36 VA, right? That's the unit. VA. So you come and replace, so meaning the active power becomes this 0.8 times 36. So we get this times 0.8. So we get 28.8. This one will be what? Know the unit, watts, right? That's the active power here. Now that we've gotten the power, Again, we are still interested in the resistance, right? Did I get the power here? Because we know when you come to this, again, this same circuit here, the power dissipated by the resistor here, R, is going to be what? The current, the same, this formula PR will be equals the current which is passing through the one, which is passing through the resistor square times what? Its resistance, right? Its resistance. So now, if we know the power dissipated by the resistor, but we don't know the what? We don't know the current that is passing through the resistor, right? We don't know IR. So to find our IR, right, there's an easy way to find this, right? You can do this by comparing the power formula, right? And then maybe doing matching, and then you can find the IR, right? You can find IR. What do I mean by this? If we were to write power, again, IR square will be equal to this. And we know that power here, this formula I wrote, or this one, let me use this one. This can also be equal to, if you were to replace this, okay, even the same formula here, right? We know it's power factor times what? The apparent power. And we know power factor is also the same as what? Cos, right? What did I get here? You divide, so you end up getting cos. So this one you get what? Cos face angle here, which I wrote here. Okay, it's already even here. So that means here I can replace here to be what? Cos. Then times here apparent power. So another S. Put here S. So this one will be times S, and we know S to be equals to, I even wrote it. So it's the same distance that I'm writing, but in a way this makes it much easier. So which is this? We get this. Of course. Now at the same time to this formula too, right? If we are writing in terms of voltage, we can say the voltage across VR, right? Over the current which is passing through this will also give us the voltage. Also give us, so if we compare this, right, we do comparison with these two here, we realize that the power here, right, with these two formulas, because here they are in parallel, right? They are in parallel, mean the voltage supply VR here is going to be equal to what? The voltage supply, which is V, right? So with this formula here, I can write P to be equals to V times R. So if we now compare these two here, which are above this end. So if you compare these two, I know this is kind of this. I'm just trying to find easier way of calculating this. So based on this, and you do correspondence, you can see that my VR, and then this one, which is V here, cos. So by doing correspondence, you can see that IR here is just equals to what? Okay, let me bring this I here. So here IR will just be equals to I cos phi. So I can go now and find what IR, right? I can calculate IR now to be equals to the power supply, which is 0.6, right? 0.6 times what? Cos phi, which is what? The power factor, which is 0.8. And this one will give us what? 0.6 rather, times 0.8. You listen. Yeah, 0.6 times 0.8. That will give me 0.48 amps. So that's the current passing through the resistor here, IR. So I can now come and replace this in my formula, right? So now I'm just going to write the power passing through the dissipated by the resistor is going to be equals to 0.48 square. Okay, you make the resistance the subject, right? We're interested and we know the power. So let me do this very well. I don't know why I'm making a mistake. So we are making here, we know the power which we got here. So we are to make the resistance the subject. So resistance here is equals to power PR over IR square, which is 28.8. Where is the power of 8 divided by now current, which is 0.48 square. Is this in the, not even getting the, this in right? Yes, so it's correct. Okay. So here we just take 0. This one square, we take it inverse times 28.8. So you get 125, right? When you do this, you get 125 ohms. So the answer for this question is A, 125. This is the hardest question, right? The hardest question under this. But we are almost done. That was question what? 28, right? Question 29. Now let's with the last question. Question 30. Question 30. Now to find question 30, a coil of resistance 25 ohms and inductance 150 millihenries is connected in parallel with a 10 microfarad capacitor across a 60 volt variable frequency supply. Calculate the resonant frequency. So I solved this question even during the Zoom lecture that we had, right? So it's the same question. I think this question was just lifted straightforward from the handout, right? Question 30, I solved it, okay? But I'm going to solve it again. Now, we are asked to find here the resonant frequency. And bear in mind that when we talk about resonant frequency, we look at it in terms of the connection, whether we are having series connection or parallel connection. So the formula for series connection for resonant frequency, when you're having series connection of the element, right? So I don't want to prove this formula. For series connection, you get this formula, or you can even call it series resonant frequency, right? Series connection. Series connection, we tend to get the resonant frequency here to be I mean FRS. Okay, when you solve this, you get here to be 2 pi and the square root of what? L C, right? I mean the square root of what? The inductance and the capacitance. That's the formula. Now if you are having parallel connection, right, especially for this kind of parallel connection here, whereby you have what? You have a coil is what? The resistance is in series what? The inductance. So meaning you have a resistor here, then you have an inductor, and then these are also in parallel to what? With this, right? So this is how this diagram will look like. Capacitor here, resistor, and this. So when we have this, you see the spiral connection. The formula for this, the resonant frequency, parallel. The formula here is this formula. It's similar to the series connection. You just modify it a bit. R, let's say parallel will be again 1 over this, but this time you are multiplying by here will be 1 over LC, right? Now minus R square over what? L square. So this is the formula, right? So you just modify this one a bit, and once you've done this, you replace the values, right? So with this, you have the resonant frequency to be equals to 1 over 2 pi. The value for the value here, we have L to be, the inductance to be what? 150 milli times the capacitance, and the capacitance is 10 micro, right? Then minus inductor resistance is 25 square. Here inductance will now be 150 times 10 to the power minus 3 this square. So this one, you just put everything in your calculator, right? You put everything in your calculator, and when you do that, right, you put everything in your calculator, then you are going to get the final answer to be to be 100. So this one 127.2 hertz, right? Yes. So you get it to be what? C. Okay, to be C. You get this in to be C. Okay, so you just replace this in the formula, then you get this answer. So that's it for today. I'll be uploading the next video at 8 o'clock p.m. Okay, so bye bye for now.